Let me start the recording here. Okay, so last time we talked about section 4.2. We talked about what a column space is. Column space of a matrix. Column space of a matrix A is the span of the column vectors of that matrix A. And now we want to talk about a null space. Okay, so and Divahar, I'll answer your question. I'll keep it there. Let me get to it a little bit later. Okay, don't worry, we'll get to it. All right, so take a moment to copy this example down. Okay, so we have here this 2x3 matrix. It's 2 rows with 3 columns, and we're letting here so it's a 3x2 matrix. Matrix A is it's a 2x3 matrix, 2 rows, 3 columns, and we have this vector U. And we want to know if U is in the null space of A. So let me go to the solution here. Just show you the solution. If the vector U is in the null space of a matrix A, then that means that A times U equals the 0 vector. That's what a vector being in the null space means. You pre-multiply the matrix, you pre-multiply the vector U by this matrix A, and it maps the vector U into the 0 vector. It maps the vector U into the 0 vector. Okay, that's the definition of what a null space is. So the null space consists of all vectors U that get mapped into the 0 vector by the transformation defined as A times U. So what I do is I take A times the vector U, and I do my matrix multiplication, and I get the 0, 0 vector. I get the 0, 0 vector, and therefore, this means then that the vector U is in the null space of A. Okay, it's in the null space of A. Okay, and All right, are there any, let me know if you have any questions on that. Okay, one moment. Yeah, it's not hard. It's not hard. And you're going to find also that the null space of a matrix is also a subspace. It's also a subspace. So like in this case, for this problem, the null space of matrix A is a subset of what space? The null space of a matrix A, in this case, is a subspace of R what? R2? So we think about the matrix A multiplying a set of vectors into the zero space. A, the matrix A, is a 2 by 3. What would the vector X have to be? What would those set of vectors have to be? What are the dimensions on those vectors X? What would they have to be? So to think about matrix multiplication, okay, we're getting some answers here. 2 by 3 times a, have to be a 3 by 1. The vector X would have to be a 3 by 1 vector. And then, of course, because that's how you are multiplying two matrices. I mean, the second matrix is a vector, but you are multiplying a matrix by matrix. And so the zero vector will have dimensions 2 by 0, or row and column 2 by 0. The matrix A is a 2 by 3, right? Matrix A, 2 rows, 3 columns. So the vector X, because the vector X, it's a vector. Good question. So James, X is a vector. Vectors always have one column. So the question is, how many rows? Well, you need the column number of the matrix A to match the row number of the vector X. That's why it's 3 by 1. And so the null space of A would be a subset of R what? R So you're taking a matrix A and you're multiplying it by a vector. A 2 by 3 matrix A, by matrix multiplication, the vector X has to be a 3 by 1. Has to be. All right, and so what? The null space is a subset of R what? Is it a subset of R1, R2, R3, R4? What's... So we agree that these vectors X here, I mean, X, for our discussion here. Okay, I'm glad I'm doing this here. X, in this case, is in what space? X is in the null space of A. Right, that's right, Matthew. X is in the null space of A. And so the null space of A is the subspace of R3. Right? So that's right, Solomon. That's right. And that's right, Matthew. So the null space is the subspace of R3. All right, good. Are there any questions on that? Matthew's good. Are there any questions? Okay, thank you, Matthew. Thank you, Solomon. Thank you, Divahar. All right, well, if there are no questions, then what I'd like to do, I'd like to go a little bit into the book here. I'd like to go into the book a little bit. Let me share the book for a moment. Hold on, let me get, I'll share it. So I want to, in the book here, go to chapter 4. Okay, and go to section 4.2. Yeah. So this is bring that down a little bit. See, you go too much and you, I don't know where I am. Hold on. Okay, so here they talk about the null space, and there's a little picture here. So you have a null space. Blow this up a little bit, bring it down a little bit. So if you have, I'm just trying to, sorry, I'm having a lot of trouble positioning this. All right, hang on. I'm gonna have to find out how to do this. I need a little more control going down, going down the page. And I'm having a little trouble. Okay, that'll work. I use my cursor. Okay. All right, so okay, so the null space of an m by n matrix is written as the null space of A. And it's a set of all solutions to this homogeneous equation AX equals 0. But the null space of A, if you have an m by n matrix A, the null space of A would be the set of all vectors that are in Rn space, such that A times X equals 0. And what they're doing here is they have a little picture of the vectors that in the Rn space. So the Rn space, the null space of A, is a subspace of the n-dimensional space Rn. And what it does is it takes, so that little line there, that just means, hey, that's a subspace of the n-dimensional space Rn. The null space of A is a subspace of the n-dimensional space Rn. And all the vectors in the null space get mapped, including the zero vector. The zero vector is obviously in the null space because A times 0 is 0. All those vectors get mapped to the zero vector. All the vectors in the null space get mapped to the zero vector, and the zero vector would be a vector in Rm space. Okay, so that's just a little pictorial representation of null space. Are there any questions on that? All right, very good, very good. Well, let's move on here. Okay, let's move on. So here, an explicit description of the null space of A. Here they say find a spanning set. This is example 3. Example 3. Find a spanning set for the null space of this matrix. So this matrix is a 3 rows and 5 columns, a 3 by 5 matrix. And so what we need to do is find the solution set for this. We need to find the solution set to AX equals 0. So when you're finding the null space, you need to solve the system AX equals 0. Sometimes what students will do is they'll get a little lazy and they'll leave out that 0 vector at the end and then provide a solution, but that's not showing work properly. Whenever you find the null space, you need to solve the augmented matrix, where you have the matrix A with the accompanied by the 0 vector. And if you, what they do is they do row operations and they reduce this augmented system A0 to this matrix here. Now, what form is that matrix in? This matrix here, what form is that in? Is that in reduced echelon form? It's in triangular form, absolutely, Solomon. And it's, well, it's in echelon form. That's right. That's what I was looking for. It is in triangular form, but it's in echelon form. Okay, it's in echelon form. And so now that it's in echelon form, okay, they actually solve it. I mean, you could put this in reduced echelon form. You could go all the way and put it in reduced echelon form if you wanted. But, you know, all right, now hold on here. I want to go to the next page. Let me see. What's this arrow going to do for me? Okay, hold on. I want to go to the next page. Okay, so I go to the next page. All right, that's fine. So the solution, the general solution here is given here. And what they do is they write the general solution in parametric vector form. Parametric vector form. So here's x1, x2, you know, x1 is this, x2 is that. I mean, they write it in parametric vector form. Well, first of all, they say, okay, the null space would be a subspace of R5 because you have 5 variables you're solving for. But then what they do is they write the general form of a vector in the null space, and then they write it out in parametric vector form. And your free variables are the coefficients, the scalars in this expanded form, and your spanning set is UVW. So that's how you find the spanning set for the null space of a matrix. That's how you find the spanning set for the null space of a matrix. Let me just see here if there's anything else I can add to this. Let's see. One moment. And the null space will satisfy the conditions for a subspace. Let me see. There's a question here. I heard something here. I didn't know. I don't think it's. No, it's not in. Oh man, you're right. You're right. So class, on example 3, yeah, I looked at it too quickly. It is in reduced echelon form. Let me go back here. I apologize. I got that wrong. This is, and thank you, Solomon. This is actually in reduced echelon form. It is. So the augmented matrix A0 is in reduced echelon form, and so Now, you find out the vectors in the spanning set for the null space of A. Okay. And they make a few comments here. The spanning set produced is automatically linearly independent because the free weights, the free variables are the weights on the spanning vectors. Okay. So, I hope that's pretty clear. I hope that's pretty clear. Are there any questions? Good catch, Solomon. Thank you, by the way. All right, we're good. Okay, all right. Well, let me show you a little bit more of this chapter before we move on. This section, I should say. So there was something I wanted to show you here. Yeah, the kernel and range of linear transformation. Okay, so they have here a picture. Well, they have a definition. Oh, no, actually, I'm right. I want to go right here. So the null space is sometimes called the kernel of the transformation. Remember what you're doing. You are taking the transformation is the set of all vectors u in a vector space V, such the transformation of u equals the zero vector. Right? That's what, and in our cases, we are, like the example we saw, the transformation of u was equal to A times u. The range of the transformation is the set of all vectors px for some x in V. So they have, again, another nice little diagram here that shows a vector space V in figure 2. Figure 2, they have a vector space V on the left and another vector space W on the right. And so the transformation takes vectors from the domain and puts them in the range. Okay, and again, the kernel of the transformation, that would be equivalent to the vectors in the null space. All those vectors get mapped to the zero vector, and then the transformation takes vectors in general in the vector space, in the domain of the vector space, and maps them to the range. So the range of space W is larger than the null space is. Well, I want to be careful. No, let me go back on that. In the vector space V on the left, the domain of the vector space V is larger than the kernel, or at least as large, let's put it that way. Because the domain, the vectors in the kernel of the vector space have to be mapped to the zero vector. But if any vector under the transformation, any vector in the domain under the transformation would be mapped into the range space in W, in the vector space W, and that's at least as large as the zero vector. So I find these little diagrams helpful. I don't know about you. Let's see, Matthew says basically the null space is the set of all vectors that are in the null space of the matrix A. That's correct. That's correct, Matthew. That's right. All right. All right. So are there any questions in general on this on section 4.2? Devahar says each null space vector corresponds to one linear relationship. Well, when you take a matrix A and multiply it by a vector U, that is a linear transformation. So the null space comes about from a linear transformation. Yes, it does. All right, let me stop the recording.